I recommend that before we begin, you read the introduction to the demo video series. In my previous demo 1, I demonstrated the design of lossless codec with Altera memory in real time. We looked at 3 examples in which I presented algorithmic state machines constructed from our GUI ISM creator, from System C and from VHDL. I will return to this ISM representation in this video too. In this video, I will demonstrate high-level and register transfer level design with our tool Syntagate, a product of Synthesa company. This tool implements the design of control and data path intensive systems with very complex control units containing numerous inputs and outputs. Syntagate performs automatic synthesis of digital systems from behavioral specification to the high level and register transfer level. The main difference between Syntagate and other design tools is that the designer doesn't need to use hardware description languages. Instead, Syntagate uses algorithmic state machines at different steps of design. As an example, we will discuss 2 designs, Super Nonsense and Washroom. I will explain the unusual names for this system. First, let's look at Super Nonsense. To test the ability of Syntagate to automatically design very complex digital systems, I gathered very different modes, operations from various designs, robot, controllers, processors, communication devices, games, etc. in one heap. Of course, nobody wants to implement such a wide variety of applications in one design. This is the reason I called this design Super Nonsense. You can find the file supernonsensealtera.zip with some folders constructed during this design at synthesa.com. Let's begin from nonsense. This is the working folder of our design. At the beginning of design we have 3 folders: initial, spec and components. The folder initial is sufficient for the design by itself, because Syntagate constructs specification automatically in the folder spec, but I have already constructed the specification. This is a very complex design. Folder initial contains 32 modes and its subfolder general 140 sub-ASMs, generalized operators. If the designer would like to use a pre-designed IP core, they must place it in the third folder, Components. In this design we use 4 memory cores from Altera. One of them. I had generated them from the tool Quartus of Altera. To design with Syntagate, we can present ISM in 3 versions: as a picture in ISM Creator, as a text in System C, or as a text in VHDL. When I am talking about ISMs in System C or in VHDL, I am referring to them as graphs presented in these languages. You can find more details at site synthesa.com, but I will return to that a little bit later too. As I have mentioned above, folder initial contains 32 modes. In Syntagate, there are no constraints on the number of modes. The design can contain tens of modes and even more. Now you see one of 32 modes, Robot Benny, constructed with our GUI ISM creator. It is in the folder initial. For more information about ISM creator, go to synthesa.com. You can even download it and try it for free. This ISM contains 3 sub-ISMs: Search Target, Sensor Start and Speed Select, yellow operator vertices. Each generalized operator should be drawn separately. This file must have the same name as the name of generalized operator in the mother's ISM. To open a sub-ASM from a Maurer ASM, right-click on the corresponding generalized operator and open, and so on. In this design we have 8 levels of inclusion. You can see the inclusions in file funcMLog in folder insert_comp, constructed in the process of the design. Using such generalized operators allow us to implement top-to-bottom design. And the designer doesn't need to design complex ISMs. As a rule, they contain about 7 to 10 vertices. The designer must put the generalized operators in folder general, which is subfolder of folder initial. When I click build in ISM creator, Syntagate immediately compiles this schematic into file in folder initial, main.rb GSA, ISM_s2 connected list, and main.rb txt. These two files are an internal representation of ISM, and Syntagate works with them, not with its pictures. From file main.rb txt we see that this mode contains 5 operators, 8 microoperations, and 2 logical conditions. To implement high-level synthesis of digital system, the designer doesn't have to define each port and signal. Syntagate's program automatically creates an XML code of a functional specification. It is in folder spec. This file contains specifications of 129 ports, 150 signals, and 11 variables. The designer only needs to insert the lengths of several ports and signals into this specification in the dialog mode. Again, not all but only a part of them. Thus, before the design, we have ASD, GSA, and TXT files in folder initial and its subfolder general, file funcMI spec in folder spec, and 4 Alteras memory files in folder components. Other files in folder spec and components will be constructed automatically in the process of design. As I explained the content of a working folder before the design, we can now begin to design our super nonsense. This is our simple interface to demonstrate the Syntagate design tool. If the designer begins from ISMs from GUI ISM creator, they must check the box ISM in section source. If from system C, check the box system C. If from VHDL, check the box VHDL. This figure demonstrates that ISM can be presented as a graph drawn in GUI ISM creator, a text and pseudocode of system C, a text and pseudocode of VHDL. In this figure on the left, you see the ISM of a main robot Benny, one of 32 mods in the super nonsense design constructed with ISM creator. The designer doesn't present the design in system C or VHDL. The center and right images in this figure contain ISM presented as a text. They don't have definitions of ports, signals, or variables. We used operators of system C or VHDL to present our graph as texts. If you compare this text with the left image, you will understand that they present the same behavior. When I am talking about ISMs in system C or in VHDL, these ISMs are only graphs presented with operators of system C or VHDL. We made these options for the case if a designer wouldn't like to draw ISMs but prefer to write them in the text file. Nevertheless, I highly advise to draw ISMs in ISM creator. Let's begin our design of nonsense with Alteras memory. I must insert the name of working folder in the section project folder of our interface. I check the box ISM as I begin from ISMs from GUI. Check the box Combine ISM. I have 32 modes in this design. And check the box Include Generalized, as we have 140 sub-ISMs in folder General. To design nonsense at the high level in RTL, I must click Run. I don't close the DOS window because I want to show that our design is implemented in real time. Let's wait a little bit. And in about 35 seconds, the design is complete. The time of design is written in the file HLS total time team. As a result, we have 13 new folders in the working folder. Each folder contains one or several stages of a design together with the complete documentation of these stages. The result of high-level synthesis is presented in folder HLS. Syntagate automatically constructs two designs at the same time. The first in VHDL, file funcmyVHD, and the second in systemc, file funcmyCpp. File funcmyVHD is a finite state machine with 588 states. Its length is 6,537 lines. This FSM presents our whole design at the high level in VHDL. File funcmyCpp is longer, 8,919 lines with the same 588 states, and it also presents our design at the high level in systemc. Now let's look at the RTL design in folder RTL. Syntagate generates VHDL codes for 73 components of the data path listed in file components VHD. At the last step of the data path design, Syntagate automatically instantiates these components in the data path, file dpvhd. At the bottom of this file, you will find that it contains 2,236 lines and 287 components instantiated in the data path. The number of instantiated components is more than the number of VHDL files, 79 files, in folder RTL, because some components are used several times. Syntagate automatically creates the RTL file of control units, file struct mvhd. The control units is a finite state machines with 615 states and 8,567 lines. At the last stage, Syntagate creates the top level file top.vhd, automatically combining two components, control unit and data path. Its length is 2,630 lines. The entity of this file contains inputs and outputs of the design systems. Once again, we have implemented the whole design containing more than 1,600 files in about 35 seconds, and at the beginning we only had algorithmic states machine and nothing else. no VHDL, no Verilog or anything else. Let's go to the second design, washroom. This is a light-hearted design example of a person or virtual robot that goes to the washroom instead of us. I hope that I won't ever need to use such a robot. It is interesting that this design passes exactly through the same stages even for it is a pure controller. Its data path is empty. You can find file washroom zip with some folders constructed during this design at synthese.com. ASMs in folder initial are clear because everyone goes to the washroom several times per day. When our virtual robot wants to go to the washroom, it performs the following. See ASMs, I will only shortly list his actions. First, if he is sitting, he must stand up, leave the room, go along the corridor, turn left or right and check that the washroom is unused. When he must enter the washroom, go into the stall, open it, enter, relieve himself, use toilet paper, flush the toilet, wash his hands and return to his room. And we can open each sub-ASM, for example, for yourself. I think you understand what he must do. Let's begin our design. First I must insert the name of the working folder in the project folder of our interface. The working folder of this design contains only folder initial. Thus, to get the functional specification, I check the box funcspec in the Syntagate interface. Since folder initial contains only one mode, washroom, I don't check the box combine ASMs. But I check the box include generalized. We have several sub-ASMs in folder general. To design washroom at the high level in RTL, I must click Run. And immediately I get the message the specifications are ready. The design is so simple that Syntagate didn't ask me about the length of any signals. It is clear why. This design is a controller without any components of data path, no flip-flops, register memory. Syntagate has put functional specification in folder spec. And in about 3 seconds, the design is complete. The time of design is written in file HLS total time. As a result, we have 13 new folders in the working folder. Each folder contains one or several stages of the design together with complete documentation of these stages. This design is very simple. The result of high-level synthesis is presented in the folder HLS. Once again, Syntagate automatically constructs two designs at the same time. The first in VHDL, file funcMI-VHD, and second in the system C, file funcMI-CPP. File funcMI-VHD at the high level contains only 21 states and 275 lines. Compare with super nonsense 588 states and 6,537 lines. In folder RTL, Syntagate generates VHDL codes with only 4 files: components, data path, struct_tem VHD and top VHD. The total number of lines in the 4 files is 433. Compare with super nonsense 79 files with 15,938 lines. In this design, data path is empty. You can find more about design methodology realized in Syntagate in my books, Finite State Machine and Algorithmic State Machines, and the second one, High-Level Synthesis of Digital Systems, available on Amazon in ebook and paperback. In the next demo, Demo 3, I will demonstrate the design of 105 projects in real time. Don't be scared. It won't take hours. We will do this in under 7.5 minutes. I will also explain how I choose examples for this 105 design marathon. I would like to underline that Syntagate allows quickly implement, check and estimate multiple design versions, find and optimize solutions for design problems, produce design documentation automatically, and simplify the digital system verification problems. Syntagate covers most digital system design from DSP to processing units. It can be used in the design of robots, controllers, processors, IoT and AI systems, digital systems for automated and autonomous cars, etc. Likewise, Syntagate can be effectively used in numerous university courses. You can get additional information from our website synthese.com. Thank you.